Okay, so welcome to the meeting number 16 in the summer version of the computational chemistry class. Summer version, so it is a little bit lighter than regular semester version, and the class includes the goals of describing the characterization of molecules and materials through computational modeling by using by providing a bit of background of theory and running correct software on correct hardware. The course is organized as four chapters, starting with building molecular models, then the chapter on the electronic structure, basic electronic structure theory, and then two chapters on density functional theory and excited states. At the end of each chapter, there are presentations by attendees who share their skills in operating the software. The goal of this presentations is that presenting skills to the peers is beneficial both to who is presenting and who is listening, and then we make sure that everyone is confident and mastering the skills, and later then they can be applied to research projects. So the schedule of the meeting is here. So there are five speakers, and I volunteer to bring up the slides. So when needed to go to the next slide, just tell me by voice. This is made in order to speed up time on the loading and unloading and sharing screens. So the first speaker, well, we will cover basic aspects of using Gaussian and Gaussview, including both mouse-operated graphical user interface skills and visual interpretation, as well as the way to operate software in a command line. So with this, I would like to invite the first presenter, Joyanta Banejee, to the stage, and the floor is yours.
Yeah. So I'll be discussing here. Could you hear me, right?
Yeah, please start.
Yeah. Thanks. I'll be discussing here a little long. The available electronic structure methods in Gaussian line, basis sets, energy optimization, and spectra. My presentation will be a little long. Next slide. Here a list of methods available in Gaussian. Like first of all, molecular mechanics. Example Amber, universal force field UFF, semi-empirical method like Austin Model 1, PM3, CNDO, INDO, RDFOC, DFT density function theory, MP2, MP3 like molar Pleasant perturbation theory second degree and third degree, MP4 molar Pleasant perturbation theory fourth degree, QCI quadratic configuration interaction, CCSD couple cluster single excitations, double excitation, and CASSCF like complete active space self consistent field, and many others are there, but still I included only that one. Next slide. Most popular methods, like most popular methods, like first of all, you can talk about um, molecular mechanics. So molecular mechanics means like potential energy calculated by force fields. Semi-empirical. Semi-empirical is based on Hurdy. Many approximation uses from parameters from empirical data, fall sort where empirical data for certain systems is not included in the database. Artifact, also known as SCF, subconsistent field, and embodied by functions, like approximated by a single slated determinant. DFT, density functional theory. So properties of many electron systems determined using functions, especially dependent electron density, mainly used for ground states. And MP2 is like improves on the Hertog method by adding electron correlation effects mm, by means of Rayleigh-Rodinger perturbation theory. Next slide. Here, how to choose different methods. Like currently, I'm using Mac operating system. So here, what I did first, I I went to I downloaded Xcode for Mac OS. It was very important to run uh, Gaussian, it's like Gaussview and Gaussian. You have to download in Mac OS Xcode. So first, the same thing you have to put in login to SSH client pre-installed, and you have to put like database, photon, clean it out of photon and all those things, and then navigate to your directory and type gview.exe. A lot of things you have to do like cd spec 001 slash, then ls cdcam 476, ls cdcam 4676 summer, ls cd your name, then pwd mkd 676, then g Gaussview.exe and press enter, and then pops up, and then open your model, select calculate on the menu bar, click methods tab, then select from menu of methods, then submit job. Next slide, please. So for calculation, you have to calculate like Gaussian calculation setup. Lot of things, lot of options are here, like Gaussian calculation setup, Gaussian quick launch, Gaussian calculation scheme, current job. So what you have to do basically, you have to Gaussian calculation setup you have to set. Next slide. So when job type, you will get the geometric connectivity like 321G, and charge and multiplicity like 301, job type, and lots of things. Job type, method, title, link 0, general guess in view. So job type, then below energy and optimization, frequency, optimization plus frequency, RC scan, stability, NM, a lot of things, NM spectra, a lot of things. So in job type, you have to choose first below in energy. Next slide. So and then uh, here after job type you have to go method. So method means like you have to calculate that lot of things are there like ground state, Shinjo, Sys, Saxi, and also TD, SCF means time dependent SCF, UOM, CCSD, and Ertifog, and you have to change it here like in right side. I'm talking about right side, that ground state. Suppose I have chosen here DFT, default spin B3 LYP. So basis set 321G. Here is showing 321G. And for DFT, here this button, you can choose like mechanics, semi-empirical, a lot of things. Previously I have already discussed. Like for mechanics, semi-empirical, Hartifog, DFT, MP2, MP4, CCSD, uh, CASSCF, DB, compound, external job, custom, and you can choose here like default pin, and uh, then also those things later. Next like this. Here, like after that, already I discussed ground state. You can choose your DFT and maybe your default all those things. But in B3 LYP, you can Also, you can change it here, like LSTA or VPV86. You can choose here also CAM, CAM B3LYP, B3PW91. A lot of things I don't know below those things. I think it's beyond of my knowledge, but I think it's for primary purpose, for learning purpose. We are discussing here B3 LYP and CAM, CAM B3 LYP. Next slide, please. So, introduction and nomenclature of basis sets. Here, in computational chemistry, it's a very important thing, like calculation of the molecular orders, MOs, right? So, using MOs, like you have to think about like energy, electron density, electrostatic potential, transition state, frequency, lot of things. Using MOs, we can cover, right? So, calculating MOs is not easy. At molecular orbitals, it's not easy. So, computer does the MOs calculation for us, but we need to provide some information first, like input files, lot of information to put. You have to put, then you will get the result. Next slide. So, polarization and diffusion functions. The most common addition to minimal basis sets are probably the addition of polarization function. Polarization function is denoted in the name of basis sets developed by John Pople by an asterisk term. For example, STO3 is term, polarized person STO3. This is polarization. Two asterisks, like double star, indicate that polarization functions are also added to light atoms like hydrogen and helium. This is two aspects. Then another common addition to basis sets, the addition of diffuse function. Diffuse function is denoted at the Pople type sets by plus sign, plus positive sign. This is a John Pople type sets, and Jheng type sets like AUG from augmented. Two plus signs indicated there are two plus signs and two Pople signs. Two plus sign indicates that diffuse functions are also added to light atoms like hydrogen and helium. Next slide. Double zeta. In minimal basis functions, only enough functions are employed to contain all the electrons of the neutral atom. Example, for the zero in the periodic table, hydrogen and helium, single S function. For first row element, 2s function, 1 p function. For second row elements, 3s function and 2 p functions. Double zeta, TZ. Doubling all basis functions. Like for the zero row, the periodic table, hydrogen and helium, 2s functions. For first row elements, 4s function and 2p functions. Like double zeta, that's why. And for second row elements, like 6s function and 4p function. That's a double zeta, dizzy. Same way, triple and quadruple zeta, 3 times and 4 times are minimum basis functions respectively. So you can think about like NZ, like double zeta, triple zeta, quadruple, quintuple, and so on, so forth. Next slide. John Pople notation. John Pople notation for the split balance basis sets, capital X, capital Y, Z, D. In the case, X represents the number of primitive Gaussians comprising each 4 atomic orbital basis functions, and the Y and Z means Z indicate that the valence orbitals are composed of 2 basis functions, and the first one composed of a linear combination of Y, primitive Gaussian functions. This is linear combination, and the other composed of a linear combination of Z means Z, primitive Gaussian functions. In this case, the presence of two numbers after the hyphens implies that this basis set is a split valence double zeta basis set. Split valence. What is split valence, triple and quadruple? The same thing. N, like you multiply n. N is equal to 1, 2, 3. Split valence, triple and quadruple zeta basis sets are also used denoted as X, Y, Z, W, Z, or maybe X hyphen Y, Z, W, V, Z, etc. Next slide. So here I'm giving one example. 6311 plus. Plus means I already mentioned couple plus positive. And CDP. So what is this actually? 6311 plus GDP. Triple split balance resistor. Triple split. Inner product of the valence orbitals is represented by 3 GTO, Gaussian type orbitals. The middle part of the this is middle part 1. The middle part of the valence orbitals is represented by 1 GTO. The outer part of the valence orbital is represented by 1 GTO, Gaussian type orbital. There is a lot of difference between STO and GTO that you have to remember. STO is letter type orbital and GTO means Gaussian type orbital. Last indicates already I mentioned couple uh, one set of diffuse functions on atoms heavier than hydrogen and helium. Plus minus means indicates one set of diffuse functions on atoms heavier than hydrogen and helium. Function in parentheses like TP. It is called like you can think of orders TP like polarization functions. Those used to properly describe chemical bonds like higher angular momentum than the valence orbital. So dp means like you f ft. Maybe you can calculate also ft. F orbital, d orbital. I'm talking about dp. Dp means function in parentheses. Polarization function. This is also a polarization function. Those used to properly describe chemical bonds, like chemical bonds, higher angular momentum, then the valence orbital. All the time higher angular momentum, then the valence orbital. Next slide. So here in when I calculated Gaussian calculation setup, then what happened? Keywords with the LIP 6T11 plus GTP, geometric connectivity, right? Charge multiplicity 0 1. Drop time method ground state. Ground state I selected ground state, then DFT, I selected default spin with the LIP. Then basis set, you can choose 6311G. Maybe you can choose later STO3G, 321G. 321G already I mentioned what is 2, what is 1. Like 2 GTO, 1 GTO already mentioned. 631G or maybe 6C11G, CCPVDQ, CCPVTZ, CCPVQZ, LAN L2DZ, LAN L2MB, SGD, DGD, zip. This you could use also. That is also LAN L2 DZ. That is also good. So I have chosen here 6311G and positive sign that already I mentioned that purple diffusion things, positive sign, and TP this is the polarizable functions parameter. So it varies completely angular momentum and polarizability. And charge also I'm selected 0, and then you can submit. Next slide. And for spectra also I didn't properly choose previous my like titanium or maybe any folder that previously I forgot to add it. So that's why results it's not showing any result. So maybe you can do it here for spectral purpose. Anymore UV vibration very like the CV Raman from I'm from India. So CV Raman is the Indian Nobel laureate. CB Raman Raman spectra, and also like you can calculate like NMR. NMR is also very astonishing tool to predict like organic synthetic or inorganic chemistry. It's very important. NMR, UV based, it's very important, and also like vibration like infrared, and you can calculate infrared. And Raman is like it's I already mentioned Raman spectra, CB Raman the Nobel laureate. It's a very critical thing. It completely depends on polarizability. Iron, like it's a mode and a lot of things it depends. So the thing is that from in Gaussview you can calculate like a lot of things. Like you can predict spectra, you can calculate energy, optimize the molecule, so on and so forth. You can do like using Gaussian 0909. You can do you can calculate the completely what you want from your prediction, like geometry optimization, energy calculation, vibrations, NMR, UVB, scanning, IR, a lot of things. Next slide. Thank you. Thanks to all, and special thanks to Jenice. Jenice helped me a lot. Thank you so much. Thanks to all.
Okay, please join me in thanking Joyanta for a presentation. And this talk is open for discussion, so anyone is welcome to either verbalize the question or type it in the chat line. So just to start, let me ask, but if anyone has already formulated question, please go ahead. Okay, so Joyanta, you presented several methods and several basis sets. Can you please comment the principle how to select method, which gives better precision and which gives quicker calculation time?
Like methods or ground state means like basis set.
Would it be correct to say that methods and basis sets at the top of the list are very quick but less precise, and if you go down to the menu, it is more precise and more expensive?
Yeah, more expensive.
Okay.
So I think you can use Hertipop. Or mechanics semi-empirical Hertipop EFT. The fourth that you can choose for cost purpose.
Okay, okay. More questions to Joyanta? If no, thank you once again. And the speaker number 2 may join in a minute, but to save time, let's go to presentation number 3. And if when Yu is will join, probably we will let her speak whenever she is available. So talk number 3 by Kristen Patnode. So suppose the calculation has been completed and the output file in the form of .log is already available on the cluster. So the question is, which important characteristics of the molecule one can extract from it and how to do it. So with this, I would like to invite Kristen to the stage, and floor is yours.
Thank you. Like Dr. Thorne said, I'll be talking about how to extract information from an already generated .log file from Gaussview. So this will be all extracted without using Gauss. All be done in the command line without the necessity of a mouse. You want to go to the first slide. So the goal of the analysis is to extract a variety of different parameters with a focus on total energy, ionization energy, which is our HOMO, or the highest occupied molecular orbital, and then electron affinity, the lowest unoccupied molecular orbital. And then with those values, we're able to determine the HOMO-LUMO gap. So I have an image as an example of if you were to do this analysis on Gaussview, what your output would look like and how to find some of those values. But then the rest of the presentation will be kind of walking through how we extract that within the command line specifically. So if you want to go to the next slide. Oops, I think there's one before this.
Should I go one back?
Yes, please. There it is. So the first step would be to actually view the output file in your terminal or mobile extern. And this is done just by using the simple more command in order to open that .log file. And then after you enter the more and then your file name, it'll expand within the command line as a very large file. You can either hit enter to go all the way through until that black box is more 100%, or you can click through as far as you'd like, hit 2, and return back to your regular command line where you're able to then continue extracting information. You don't have to manually go through the entire file in order to be able to extract the data, but you do have to open the file to begin with in order to extract the data going forward. So next slide. So here we have the command that we're going to be using in order to extract information is the grep, G-R-E-P, which essentially just tells your computer to search for a specific word within the file. So the part that follows that, the total energy is going to be SCF, which stands for self-consistent field approximation. This iterates orbital equations until consistency is achieved. And so in this way, we're finding that overall, that total energy is going to be equal to the RHF energy that we saw above in the Gaussview output. And then again, you'll have your file name and the .log file type. And I have kind of that image there as an example of the output. And as you see, E with that RHF was the exact same as we saw just above in the Gaussview output analysis. It's a little bit quicker than that. All you do is type one simple command after opening your file, and then you get that same information. So the next slide is going to look at how to extract ionization and electron affinity. And this is done with the same grep command, which is again searching for a specific word. And then here we have either oct or virtual. So the oct is short for occupy, which is where we'll get the HOMO value. And then the virtual is going to be our LUMO value, which is our electron affinity. And so again, I have the outputs exhibited there. And the very last number from the grep oct command is going to be our highest occupied molecular orbital. So that's the value we'll use going forward for calculations. And then with the electron affinity or our LUMO, the very first value is the one we'll want to use as that's the lowest unoccupied molecular orbital. This can also be measured just in the lab using cyclical countmetry. It's typically done with just a silver chloride electrode. It's a pretty standard procedure to determine these sorts of values experimentally, but it's also possible to extract these values using our Gaussview output files. So the next slide, we'll look at how to determine the homogeneous gap, which is just a simple subtraction. And like I said, we want to focus on the last value from our HOMO and the first value from LUMO in order to determine the difference between the two. It is LUMO minus HOMO, which ends up, in this case, being about 0.4 atomic units. And this electron gap is actually used typically to determine color. It's depending on the value, the larger it is, the more you kind of get into like white. So kind of believe like titanium dioxide will have a relatively high homogeneous gap value, and that is obviously very white and opaque. But as you get into smaller values, it's going to get into more transparent colors. We also typically convert this to electron volts, but I'll get to that in just a minute. I'd like to take 1 second on the next slide to talk about just the HOMO-LUMO values in general. And this is just coming from Krugman's theory, which states that in a closed cell Hartree-Fock theory, the first ionization energy of the molecular system is equal to the negative of the orbital energy of the highest occupied molecular orbital. I just have a nice image to kind of clarify what that looks like. And then in that green, that band gap is the value that we just calculated. So the following slide is that conversion that I mentioned just previously. And that is to convert the hormonal gap into electron volts, since this is typically a more digestible number, and it's how we actually are able to relate it to the color that I was mentioning, how the size of that value says it's 10.8. That's a pretty large value for a hormonal gap, and that would indicate that it's going to be more opaque and towards the white side of the spectrum. Then before I close, I'm actually going to touch on density of states for just a second. So this is still related to the topic, as we can extract density of states PDFs from the .log file. So the next, there is. Here first I just have the definition, where density of states of a system describes the number of states per interval of energy at each energy level available to be occupied by electrons. I have an equation there. Essentially, it's defined as the sum of contributions from each orbital. It also, excuse me, important to note that a high density of states at a specific energy level will mean that there are many states available for occupation. So the general density of states is an average of the space and time domains that are occupied by the system. The next slide, I have such as kind of an overview of essentially what density of states are. And the next slide looks at how to generate the PDF plots from log file. And so it's a number of commands to use in command line. The first one being this Perl command. And then it has a variety of numbers. It's a rather long command, but the first I want to point out that the number 1000 you see, that is a smoothing number. So it affects what the output plot looks like. The 0.1 value is the resolution, which is very important for how well you're able to actually see the plot. And then the 5 and 5 are ranges for how far below and above the homonymous values the axes will go. And so on the bottom, I have 3 different images with kind of increasing those numbers to go further and further from the homonymous. As you can see, more plot is changing, and those axes are expanding to much larger numbers, and that's why we're seeing the differences in the plots. And then the remainder of the commands are just how to actually get this data into a PDF and onto a personal computer. I guess after that very last statement, you can download it and view it as a PDF. You would just follow it up with a secure copy command in order to download that to your personal computer. Now, the last slide, just to kind of summarize, once we have already generated a .log output file from Gaussview, it is possible to pretty easily extract a lot of valuable data without having to even use our mouse. Like we kind of already walked through, total energy, ionization energy, affinity, as well as that homonymous gap are all extracted using just one command. And then density of states figures are also possible to be extracted from the .log file through a sequence of commands. Then those files are able to be viewed as PDFs. And with that, I would like to open it up for questions.
Okay, please join me in thanking Kristen for a useful presentation. So,
Kristen,
yeah, please, go
I have a
ahead.
question. Could you please go the DOS like figures? Back, go back. Not DOS figures, like previous slide. Density of state, previous slide. Yeah. Or means like I'm not getting properly. Like in here, density of states of a system describes the number of states per interval of energy at each energy level that are available to be occupied by electrons. So, what is the equation below? What's the meaning? Like, what is the summation delta E minus E I sigma? What is the meaning of
Sure.
N
So,
sigma?
Yeah, so it's a little bit harder to read below, but it is denoted in the text that it's showing the energy of. So you're asking about which part? You're asking about the sigma?
Why total summation, and what is the difference here? Like delta into E minus E I sigma. So once sigma is equal to alpha beta, And what is the total energy? Like, what is this? Is approximation, right?
Yeah. So the delta E minus E naught is an energy level. It's a density approximation that's been normalized.
Okay.
And so we use in order to then generate the summation of those values across every contributing orbital in order to determine the overall density of states for the entire system.
Okay. And what is the case over here? Like jth case. Okay, what is the case over here? What is the case? Jth case. What is the case over
here? I believe it is borrowed from the material in class in the next couple of weeks. So
okay.
And Levi is answering it in the chat line.
Okay. Thanks.
It's quantum orbitals.
Okay. Thank you so much. Great.
Kristen, there is a question from Levi Lystrom in the chat room. So he's asking, why do you use -n flag in the grep -n virt star.log? Levi, can you please tell which slide was it? Or just type. When you were finding the homoluma gap. Okay. Kristen, do you remember which slide was it? I think here.
Yeah, so I know that in a variety of Linux commands that have the minus n as essentially a classification for where to start looking in the file, I wasn't able to actually find what the n is stands for. But I know it's essentially a specification for where to begin looking in the file. That's my understanding.
So it just types the number of line. Levi is typing, if you look before the column, that will help. So it's number of line in the file. And Levi is typing yes, it tells you which line of the file the output comes from. More questions to the speaker? More questions 1, more questions 2, more questions 3. Okay, let's thank Kristen once again. So let's check if you didn't connect it. You didn't connect it. So we'll go to the presentation number 4 by Mahima Murali, and the question of density of states is extremely important for all of us and for the course. So if more than one presenters do have materials, please do not skip it. Do present it, because we will be using it for the research projects in what follows. So we'll go to the presentation number 4. And Mahima, floor is yours. Let me know when you need to, when I need to flip the slides.
Yeah, hi. I think Kristen already explained how to do this density of states log files.
But still, please present and explain it.
Yeah, so for the next slide. So the density of states means as a system describes the number of states per interval of energy at each energy level that are available to be owned by electrons. So this is the command for the Perl file. So you can put the file names here, and this is the optimized log file, and the right side you can see the parameters for the Perl. And next file Next slide.
Mm-hmm.
So in the next slides, you will see the outputs. When we are done with the job, you will get this output. This is an example. So you will see the HOMO-LUMO energies and the energy gap. You can see it from here. And the below image is the output in dox.log file. And after you're done with this Perl, and you will get like this. Next slide is the conversion I'm plotting. And after, so this is the first one is the command for the download plot on Excel file. You can put a file name and .log dos.log is the command for the Excel file, and you'll get an image like this, the left one. And to download as a PDF file, you need to use the third command file, and you can find out the log file as like this on the right side.
Just a second. I need to restart the slide. It was a.
What?
Just a second. I will rerun the slide. It was a little technical delay.
Yeah, it's not showing in my system.
It's not showing in my system as well. Just wait. It should show.
Yeah, now it's came.
Okay.
So this is how the output, the Excel and the PDF file will look like when you use these three commands. So I think it's pretty simple.
Okay, yeah, many thanks. And let's go to the beginning of your presentation. It's just started from this point, but let's go to your main subject of the symmetry groups. Okay.
Yeah. Okay. So from here. Okay. So symmetry in groups. So today I will talk about how to calculate the symmetry groups using the Gaussian software. So molecular symmetry in chemistry describes the symmetry present in a molecule and the classification of molecules according to their symmetry. The symmetry point groups means it's used to describe a molecular symmetries and as it condensed representation of the symmetry elements of a molecule may possess. So this includes both bond and orbital symmetry. So this is actually the point group symmetry is actually 3D representation of a molecule using many point groups. So the right side image will use like if we know the molecule linear or whichever particular molecule, we can find out the point group of a particular molecule. And next slide. So this is, I just this is not coming into my system.
No, it is showing water molecule.
Oh, okay. So this is just I find out the point group of the point group. It's showing C2b. Next slide. This is another example for the point of benzene. It's you can see in the below. You'll see the D6. That is the point group of this benzene. Next slide. And in the Gaussview software, use an edit option, you will see the point group and symmetrize the point group, and we'll select a point group, and then next slide. And in this dialog box, you can enable point group symmetry. So we'll enable the point group symmetry, and next slide. So this is, I'm just showing how to do the calculations, how to do this symmetry, how to do this with the Gaussview. And when we enable the point group symmetry, you can see all the subgroups that are involved in D6H point group, and you can select any point group from subgroup from here, and I selected C1. Next. Next, you need to constrain to subgroups, and you need to change all changes. Click on that one. And next slide. And next, we need to optimize these bonds. So go to the bond type and select atoms, particular atoms, whichever you like, and then we'll change the bond lengths and bond types, displacement and everything. Next slide. And here also we'll change to 2.220 to the bond type. Next slide. And we'll get the approximate high order. So we'll select up. There's one more is missing, I think.
Should I go back or forward?
Yeah, so we'll get the constraint symmetry, and then we'll get the approximately high order point group. So next slide. So we'll get the set, we'll set the tolerance. So we'll go to the default one, and we'll always choose the high order point group. Next slide. So in this one, it's showing the C2V point group. We change the bond length and this tolerance, and we'll select D6H, and we'll symmetrize. Next slide. And after we done this job, we'll calculate the Gaussian using, next slide. And we can use the ignore the symmetry and calculate this one. And after calculating the energy determination, we'll get like this. Next slide. So no symmetry calculation will get the job time is 1.8 seconds, and with the symmetry calculation is 1.5 seconds. Next slide. So when we are calculating using the Gaussian, the symmetry is the logbooks will be like this. Next slide. So symmetry in Gaussview. So to control symmetry in Gaussview, optimize geometry of a molecule, and symmetry in Gaussian is reduce the time while maintaining accuracy. That's how I can find out when I did this using this software. That's it, and thank you.
Okay, please join me in thanking Mahima for a deep and interesting presentation.
I'm just showing that how to calculate the symmetries using this software only, and how do I run.
Yep. So any questions to these presentations are encouraged and welcome.
Yeah, I have a question.
Please.
Could you please go slide energy calculation of benzene with symmetry and no symmetry.
Okay.
Yeah, previous slide. Yeah. Yeah, that is. Suppose here calculate symmetry in Gaussian total energy determination. Total energy determination for benzene Hardy-Fock method 321G basis set. It's fine. No symmetry calculation. Job time 1.8 seconds. Energy is minus 229.4 atomic unit. And symmetry calculation of job time 1.5 seconds. Energy is minus 229.4 atomic units. So there is no difference in energy, and job time also difference like 0.3 seconds. So what is the conclusion you could draw from those time and energy? What's the main conclusion you can draw here? The time doesn't matter here, right?
Might be.
Wait. Joyanta, this small molecule, of course, for small molecule, it is very ridiculously short calculation time. But if one is going to compute something with like 1,000 or 3,000 atoms, then each second counts. And if the job is running 4 weeks or 5 weeks, even if it is a small fraction, it could be a big difference.
Okay, thanks, Dr. Dimitri. The thing is that here is the benzene is very small molecule. That's why there is no time difference. Like you could think about 1.8 seconds or maybe 2 seconds. That doesn't matter here in benzene case. But if you could increase the molecule size, then that could be a difference between energy, right?
One should count not the absolute time but percent. So it is 20% quicker with symmetry.
Okay. And the thing is that in all the time you have to lower the symmetry or higher the symmetry?
Higher the symmetry, right?
Higher the symmetry or lower the symmetry? Dr. Dimitri, what could be the answer? You have to higher the symmetry or lower the symmetry?
Please repeat the question.
Question is that suppose any molecule proton structure to exact structure. What could be the symmetry? You have to take higher symmetry or lower symmetry?
There are symmetric molecules, and if it is possible, one can try to use this option to speed up calculations.
Okay, thanks.
So there is a question from Levi Weistrom. With many atoms, are symmetry arguments valid? If there are many atoms, would they stay in a high point group or go to a very low point group? Mahima, do you have an opinion?
I am not sure. I think just would they stay in a high point?
Well, one may start with.
Yes? It depends upon the molecule and the. I think it depends upon the molecule.
Okay. So if one is going for optimization, it may break symmetry. But if it is some objects are highly symmetric, like fullerene, one can try to use the symmetry for carbon nanotubes.
Yeah.
Okay. More questions to Mahima? If
no, nice lecture.
Okay. If there are no more questions, let's thank Mahima once again.
Yeah, great.
And we do have Dr. Zheng connected. Would you like to present your slides?
Yes.
Okay. Do you have camera and microphone enabled?
I am in live, so.
Oh, okay. Yeah. Then it's not allowed. Yes. Okay, let's go ahead. And tell me when I need to flip the slides.
Okay. So today my topic is to address 3 questions: how to prepare a Gaussview output log file without Gaussview, and how to specify memory and number of processors, and what are spin and multiplicity input. Next slide. Let's start with the first question. To prepare output log file, there are two steps. First, we need to prepare Gaussview input.com file by using Babel command that can convert XYZ file into .com file. As you can see, after we input the command in the red box, .com file is generated. Here are the lower part is the results. And next slide. The next step is to convert input.com file to output.log file. This is achieved by typing the command highlighted in red. Here are the results. As you can see, the output log file is generated after we type in the command in the red box. To get the command in the red box, we can just use which got G09. And so, next slide. To specify memory and numbers of processes, we can use bi command to edit .com file. After typing the mproc shared, we can specify the numbers of processes. And after typing MEM, we can specify the amount of memory. The results are showing in the red box. Next slide. The charge and multiplicity are already shown in the .com file. Here, the charge is 0, and the multiplicity is 1, indicating that there's no unpaired electrons, and thus the spin is 0, and the multiplicity is 1. The value of spin equals half of the number of unpaired electrons, and the multiplicity is equal to 2s plus 1. So that's all. Thank you for your attention.
Okay, yeah, please join me in thanking you for a nice and concise presentation. So are there any questions to the speaker? So I have very general question. What should one do if? Let me go to slide number 3. So if the command in the red box takes a long time, if it uses substantial numerical resources, because Photon is very small desktop server. So what should one do if one needs to compute large molecule for a long time?
Use a better server.
Okay. And does anyone want to give a comment about clusters and so-called job scheduler? Especially, I believe Jenice may give this comment and answer this question.
Yeah, so essentially it depends on what cluster you're using. So if you're using the photon.chem server, then you would use a different command. I'm not sure if they use qsub there, as I don't know how to submit jobs with Photon, but I know how to submit jobs with CCast, and that would be qsub, your file, and then a couple of other such commands and such. Yeah, so you can add arguments to that, whether it be wall time, what processors you want, etc. But if you already have them in the file, then you can just do a quick qsub and then the file name, and then it'll just directly upload it to CCast servers, depending on which cluster you're using. So be mindful of what cluster. Yeah.
Okay. And anyone wants to give comment on what is the difference between cluster and server? Jenice, maybe you can address this question as well.
Okay, gotcha. I was just curious. I just wanted to give some time to answer as well. But the difference between a cluster and a server. So a server gives you access to a wider range of resources. Essentially, it gives you access to the clusters, but clusters themselves are different sections of a server. So let's say you connect to the CCAS server, they have different clusters, such as the home server, they have calculation servers, etc. And so you have like file space clusters and computational clusters, etc. So the server, you connect to the server, which just gives you an access to the clusters, and the clusters are where you actually do your jobs.
Okay, yeah, thank you, Jenice. I will reformulate the answer because later on we will need it practically. So yes, the server is a single box. It's like a desktop computer or a thin blade which looks like pizza box, but server is one computer, and cluster is a team of computers. So like a number of computers that work coherently. And for high performance calculations, when one needs to do something advanced and complicated, one needs a cluster. And there on the cluster, the job is, through this job scheduler that Jenice did mention, is distributed over several CPUs and several nodes, several compute nodes. So the single standalone server is not designed to do expensive calculations. So it's only quick learning. Make sense?
Yes.
Okay. More questions to the presentation by the speaker, by you, Zheng? If no, let's thank the speaker once again. And we are going to the last but not least presentation by Jenice Amb. And let me know when I need to flip the slides.
Okay, yeah. So today I'll be talking about isosurface generation and what types of isosurfaces you can create in Gaussview and other calculation setups. Next. So this will be the basics of isosurfaces, where we'll talk about molecular orbitals, formchk, cubegen, and an introduction to isosurfaces. Next. So molecular orbitals, this is a very, very basic overview. I'm not necessarily going to go deep into theory, but essentially the very basics of it is it's a function showing the possible locations of electrons in a molecule. So when you're talking about molecules, you can have multiple calculative approaches to molecular orbitals. One of these approaches is Hartree-Fock, restricted Hartree-Fock, density functional theory, or you could use linear combination of atomic orbitals to calculate these molecular orbitals. The picture to the right is a case for restricted Hartree-Fock, where you have the Fock matrix, MO vector, MO energy overlap, and then the MO vector. All right, next. So now we'll talk about the commands that generate these calculations. So formchk, this finds the expansion coefficients associated with whatever method is chosen, whether you're using Hartree-Fock, DFT, etc. And so to do this, all you do is you type in formchk and the check file that you have associated with a calculation, and then it will generate the coefficients. It finds the expansion coefficients. And then from there, you can use that fcheck file to create or generate cubes or cube files. Those cube files are the actual molecular orbital functions. So they will essentially be the thing that you use to generate isosurfaces in Gaussian for molecular orbitals. All right, next. So Isosurfaces. Isosurfaces are a plot of points of constant value within a volume. So essentially what this is we use a function. We use a 3D function, and we can take a different constant value, and it will create a surface. So if you tell the function, or if you plug in a certain value into the function, it will come out with a surface. So once you find the surface, then that's essentially your isosurface. So iso stands for 1, which means like a constant, and surface just, it's a general like volume or a surface as stated. So next. So we'll talk about setup for open shell configurations. It's very similar for closed shell configurations. Closed shells are a lot easier, and so I decided to do an open shell configuration setup, as it'll be a lot more in depth. And so essentially we'll be talking about setup for systems with spin and multiplicity. Next. So first, what you have to do is to check your charge and multiplicity of your file. Of course, you have to create a molecule first to check charge and multiplicity. But let's say that we have let's say we have 6 molar molecules around a charged titanium atom. So essentially, we will have a charge of 3 plus on the titanium atom, and this gives the whole system a multiplicity of, or a charge of 3 and a multiplicity of 2. And so you have to input that into the file and ensure that it's proper, or else you'll end up with the wrong calculation and you'll end up with wrong bond lengths and energies. Next is to complete an optimization or any sort of calculation that will produce a .check file. So you can do an optimization, a energy check, etc. It's better to do an optimization because that will give you your energy regardless, and it will optimize bond lengths and angles. So it would be a lot more rigorous to do that approach. Right, next. So completing formchk and cubegen. Like I said before, you use formchk to create fcheck files, which will be used to create your cubegen files. In this case, there are 2 states that your electrons can be in, which is alpha and beta. So it's the different types of spins that you have. So where alpha is 1/2 and beta is -1/2 spin. So since you'll have this orbital splitting due to your charge and multiplicity differing, you'll essentially end up with alpha occupied, beta occupied, alpha virtual, and beta virtual. And they will have different numbers for each type of molecular orbital. So as you see in the bottom right there, we have 35 occupied alpha orbitals, 34 occupied beta orbitals, 65 virtual alpha orbitals, and 66 virtual beta orbitals. And so these differences in numbers correspond to the fact that you have free electrons, and they will have different states depending on what orbital they're in. And so above is the CLI approach. So there's a CLI approach where you use a command line interface and you have to type formchk and cubegen. But there's also a GUI approach, which is a graphical user interface approach. Essentially, all you have to do is go into Gaussview, you go to results, click on surface contours, click on cube actions and new cube, and then it'll show the thing on the bottom right, and you will type molecular orbital or whatever sort of isosurface you want to generate. Then you click on the orbital type or whatever surface you want to generate. So then you can press OK, and it'll generate it slowly. And once it's done, then it'll show up in the sort of main box. So next. In Gaussview, which is the main service that I would use, you can also do this in Avogadro. I'm not sure if Vesta has that, as I'm not as proficient with Vesta as I am in Gaussview and Avogadro, but you can create contours or surfaces of these molecular orbitals. So in Gaussview, if you're using a CLI approach, in the Surfaces/Contours tab, click on Cube Actions, or I meant to say GUI approach, apologies. But if you are using GUI approach, all you need to do is once that the thing is generated, you just click on it and go down to Surface Actions. Once you get to the Surface Actions drop-down box, then you press New Surface, and then it'll create a new surface based off of whatever cube you've clicked on. So you notice how it has a black line over it. That means that you have that selected cube, and you can then create a surface based off whatever you click on. For CLIs, for the CLI approach, you need to go to Cube Actions and press Load Cube, and then you can select which cube file you'll be using, and then all you need to do is click on it, make sure that black line is over it, go to Surface Actions, and produce a new surface. Or if you want to produce a contour, it's pretty much the same thing. All right, next. So types of surfaces and charge analysis. So we'll be talking about molecular orbitals, electron density, spin density, and electrostatic potential surfaces, along with Mulliken charge and DOS plots, though it was covered in much more detail in previous presentations. It's good to touch on how to plot density of state graphs, just very simple command line based stuff. So next. So for an MO isosurface, the top picture shows the alpha molecular orbital from the previous calculated setup. So this shows where your spin 1/2 electron is, and for the lower case, for the lower one, it's your beta molecular orbital states. So your alpha molecular orbital in this case is going to be your HOMO, and the beta molecular orbital in this case is going to be, I'm sorry. Oh yes, okay, sorry. So they're both HOMO states. So these are your highest occupied molecular orbital states. And LUMO can also be plotted. It's very similar to this, just, differing look, essentially. So next. All right, creating other forms of isosurfaces. Other common isosurfaces are electrostatic potential, electron density, and spin density. Can be done via CLI or GUI prompts. So for CLI, the commands are above. You have to have a, let's see here. You do have to have an fcheck file on hand, so you need to do an optimization or any rigorous calculation to ensure you get the molecular orbitals. So you need an fcheck file, and then you can take cubegen, O, density, or spin, or potential, and just plug in whatever command you need, and you can see all the commands up in the top picture. Whereas with GUI, it's very similar. So all you do is you have to generate cubes, like I showed you previously, and instead of doing molecular orbitals, you type in total density, spin density, or electrostatic potential surfaces, and that should get you to where you need to go. All right, next. So for electron density, this shows where electrons are probabilistically found in the molecule, and essentially it'll just show you the general probabilistic location of where an electron could be in the molecule. Of course, these aren't 100% accurate, but they're fairly accurate. So the ISO is a little screwed up in the picture that I took, but that's fine. That gets the point across. All right, next. So spin density. Spin density shows where excess spin is localized. So these are mainly for open shell orbitals. This applies to molecules with open shell or radicals. So in the right case, it's a radical molecule, whereas with the left case, it's just with open shell. So this is only when you have excess spin. If you have a no spin complex, then you're not going to end up with any spin density. So in this case, this just shows where the excess spin is, and it shows you, in this case where the extra beta orbital was in the left case, and in the right case, those are radical orbitals. So, all right, next. So for electrostatic potential, this one, instead of a regular surface, there's a mapped surface, but you can do it in different ways. So for the molecule that we had calculated previously, I used a regular surface. So that's why you just see yellow there and no other colors. That's just a regular surface. Whereas you need to use a mapped surface to show anything very rigorous. So for the top part, which is chloromethane, it shows the electrostatic potential map. So of course you see how red is most negative and blue is most positive. So essentially it'll be showing you partial charges on atoms and exactly what sort of color they take. And that'll be shown by a mapped surface instead of a regular surface. So to properly calculate this, like previously, you need to click on the cube file that you generated, and then instead of clicking on new surface, you produce new mapped surface, and then you can change parameters based off that. All right, next. So Mulliken charge analysis, all you need to do is you need to produce a molecule with a check file. All you need to do is click on Results tab in Gaussview and click on Charge Distribution. Once you've clicked on Charge Distribution, you just, in the window which is on the top, you need to make sure to show numbers and color atoms by charge, or else you won't be able to see the numbers or any sort of color denoting what sort of, charge it is. So ensure to do that. And you can also see Mulliken charge based off of your check file. All you need to do is do a more, and then your check file name, and then you'll be able to scroll down and search for your Mulliken charges, and that should be good. All right, next. So this is just a very, very brief overview of DOS. This isn't at all very rigorous as was previous presentations, but it's good to know just general format, especially for differentiation with alpha and beta spins. So for making a DOS plot, you do a Perl and then the rest of the command, and that will give you your alpha or beta .log files. And in this case, the parameters were 1000, 0.1, 3, and 3, and those were described by Kristen in her presentation. And so you can change those parameters based off what you need. I forgot to put them in the text for this slide, but yeah, as you can see in the top portion or in the top picture, you can see the parameters are there. And you can change those parameters based off what you would like. As for files, so it will rename your files, or it will create .log files based off of the file that you put in. So in this case, I put in TIO6H12_charge3 yada 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 .log. In this case, it will name it to TIO6H12_charge3 yada 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 alpha.log. So you need to change your file name to DOS_alpha.log or DOS_beta.log based off what code you're using. In this case, for the code that we're using to generate the plot, it needs to have input files named DOS alpha and DOS beta. So you need to make sure to rename your files to those, or else it won't work, like so shown in the second picture where it says warning skipping unreadable file and skipping unreadable file and no data in plot. So you need to make sure that you rename your files to DOS alpha and DOS beta. Then just use GNU plot command to plot both new log files as shown in that second picture, and next convert PS file to PDF using PS2 PDFWR command, and then you are totally able to view the file created, and it will show the plot in the bottom picture there. So next, that should be it.
Okay, so please join me in thanking the speaker, Jenice Amb, for informative presentation. And the talk is open for discussion and questions. So please speak or type the questions in the command line. I'll start. Jenice, at the very beginning, maybe slide number 3, you were showing the examples of orbitals right here. Oh, no, too far, too far. So, would you please comment if it sounds familiar to you, what are the bonding and anti-bonding molecular orbitals, and which of them are typically occupied, which of them are typically unoccupied, in which systems one can see them?
Yeah.
We'll answer the question of you, Zheng, later. Do you have comment on bonding, anti-bonding?
So unbonding and antibonding. So for, are you talking non-bonding and antibonding, or did you say bonding and antibonding? Sorry.
Bonding and anti-bonding.
Okay, yes. So bonding and antibonding. So bonding orbitals are those that are properly bonding, electrons. So essentially that's what creates your bonds, whereas antibonding are the essentially opposite of those. So you can think of it like destructive interference and constructive interference. So constructive interference is when you get a bond, and that's where you have phase overlap, and the electrons are able to sort of coalesce into these orbitals. Whereas antibonding shows the destructive interference that's possible with these orbitals, where they're not able to overlap because their phase is different. So then they'll destructively interfere in the middle, and so you'll get an antibonding part, and that can take away bonds as well. So
which of them are shown here in this example?
So in this case, the virtual ones are going to be your antibonding, and your occupied states are going to be your bonding orbitals. So the virtual you can tell because you have these phases that are completely different, that aren't overlapping, and they're creating these sort of distinct packets of sorry. What do you call it again? I'm sorry, I'm having trouble with my terminology today.
That's fine, that's fine.
But it's creating these sort of packets to where these phases are not connecting. Whereas the occupied states, you can see that there's like a big red blob and a big blue blob, and they are connected essentially. And so those are your bonding states essentially. So they create constructive, and then the virtual is destructive.
Very good, very good.
I think, Jenice, in my view, you could say one thing, like in constructive and destructive, like occupied orbital, could you please check if that nodes, like occupied orbital, just one node, but in virtual, you could see here 2 nodes, right? One,
Yes.
2, 3 nodes, right?
Yes.
1, 2, 3. So that's why it should be anti-bonding, like virtual.
Yes.
Nodes increasing. So you could think about nodes. So nodes are increasing means that could be definitely anti-bonding.
Yes.
Right?
Yeah,
nodes
absolutely.
means like nodes, electron density 0, like nodes. So that's why you have to think about nodes, like and you could easily differentiate between occupied and virtual. I think so.
Yes. Yeah. And that totally makes sense. I just tend to think about it a little bit differently, is all. But yeah, that's a more rigorous terminology.
Terminology means I think you could think about like occupied means like this is constructive, and like destructive means like virtual.
Yes. Mm-hmm. Yep.
Okay.
That totally makes sense. Yes.
So you, Zheng, was asking what does SCF mean, and Mahima did already answer. So would you please comment if you echo, if you confirm, and comment on this SCF?
Yes. So SCF is self-consistent field methods. Yes.
So self-consistent field of what?
Oh, self-consistent field of. Could you go to the slide? Did I mention that in the slides?
I may have missed it. Which slide would you like me to go to?
I have no clue. I cannot remember where I.
I think the slide that is being shown here is okay.
Okay, the side being shown here. I'm honestly not 100% sure. I know that it is self-consistent field method, but I could not tell you the actual method that it uses, as I'm not necessarily knowledgeable in that aspect.
Do not worry, but just give you a first impression. Field of charge density, field of photons, field of electromagnetic field, like field of what?
So I would probably say it's an electromagnetic field, as that would probably give the calculated results for a basis set, I would guess.
So electrostatic field created by the electrons distributed over molecular orbitals.
Yes.
Okay. Okay. Good. Are there more questions to Jenice? Questions 1, questions 2, questions 3. Okay, if there are no more questions, I will give a brief concluding word. So, many thanks to all presenters and all participants of the discussion. So, the talks provided important, vital skills for operating Gaussian software. So from now on, all presenters are entitled as certified experts in Gaussian and Gaussview software. In the next weeks, we will start completely new software. But when we will go to mini research projects, some of you may decide to use Gaussian software as a tool towards addressing your research questions. And with this, let me thank all speakers and participants once again. And with this, the meeting is over. Everyone is welcome to disconnect, and all presenters obtain a credit equivalent to 3 successful homeworks. Looking forward to see you next Monday. Have a nice week and weekend. Done. Oh, thank you, Raju, for feedback. Yep. See you.